Hello, this is Mr. Gilmore with the 13.1, the Analytic Formulas. We are moving now out of synthetic geometry, which is what we've been studying this entire year, into what we call analytic geometry, or another name for it, coordinate geometry. So let's begin by talking about the difference between our synthetic geometry and that of the analytic geometry. So synthetic geometry is a name for the variety of what we've really studied for this point, which remember begins with definitions, moves into postulates, and then into our deduced theorems. Whereas with the study of our very short study, I should say, of our analytic geometry, this is the geometry that involves the coordinate plane, which you're familiar with the coordinate plane as the XY axis, which is essentially then geometry fused with our approach from algebra. And we'll see then as we unfold the importance of today's lesson with our three formulas, with these analytic formulas, we'll be looking at our 2 points in a plane and taking those out of our synthetic plane and placing them in our analytic plane. So, where our studies began, way back at the beginning of this system, it began with 2 points. We introduced what a point was, and we introduced that through a second point, there exists a line. And that's where our adventure began. So, through any 2 points, there's just a line. That line is, in fact, unique. And from that line, we then also may produce a segment. Now, there are 2 guarantees that we learned about segments. Every segment has a length, and every segment has a midpoint. We're going to carry these ideas into our analytic or coordinate approach when discussing these 2 points. Because what we can do then is, what if we then took those 2 points and we placed them in a coordinate plane, which essentially is plotting them a relative distance from a fixed point, which that fixed point is the origin. What we then do is we introduce the coordinate plane, which should be relatively familiar to a lot of you guys. When we encounter 2 points in a plane, we know that we can assign those 2 points an ordered pair. We call those x sub 1, y sub 1, and x sub 2, y sub 2. And what we're going to explore then is the ability that we have with 2 points in a coordinate plane. We can actually find the length of any of the given segments from those 2 points, because remember, we're guaranteed length for every segment, and we can actually calculate the midpoint of every segment, and we can do that as well with 2 points in our coordinate plane. So we're going to be introducing our 3 analytic formulas today. We have methodical operations or calculations that we're going to be using to calculate length, midpoint, and then a new insight to a line, which is what we call slope. Now, again, don't fret, okay? We have formulas for all of 3 of these. So we'll be investigating the 3 formulas, and then we'll be putting these formulas into practice. So, distance formula. Every segment has a length. So again, let's let our 2 points A and B be the A such that it is the ordered pair x sub 1, y sub 1, and B such as x sub 2, y sub 2. These are going to be the endpoints of this segment. What we then produce from this is what we call the distance formula, that the length of AB, right, the length from point A to point B, is then essentially the Pythagorean theorem in the coordinate plane. So we have this very large square root of the difference of our x values squared plus the difference of our y values squared. And from this, we're actually going to be able to produce the distance or the length of any segment. Now, we're going to use this in a moment, but you want to take a moment to make sure you write this down. You will have access for this during the chapter. It's on your postulate theorem handout. However, it's a good idea to have this written down, especially when diving into the homework assignment. We also have the midpoint formula. That again, if we let our 2 points A and B be x sub 1, y sub 2, and x sub 2, x sub 1, y sub 1, and B has x sub 2, y sub 2, then we find our midpoint to be this, that it's the average of each of the coordinates. So we take x sub 1 plus x sub 2 divided by 2, and then y sub 1 plus y sub 2 divided by 2. So this is then going to produce the midpoint of that given segment. So every segment has a length, every segment has a midpoint. Through these 2 first analytic formulas, we can then calculate those. But we have a new insight to a line called a slope. So by definition, the slope of a line is the change in the y over the change in x. The value of the slope describes in a very rough form the steepness of the line. And so when we calculate slope, we're actually going to find there are 4 types of slope that we'll encounter. Let's take a look at those first before we look at our slope formula. So the 4 types of slope boil down to this. We can have positive slope, negative slope, zero slope, and then no slope. So positive slope is when we read our graph from left to right, that the equation of our line is going to be moving up and to the right. So we have this then slope up form when we see positive slope of a line. A negative slope, as we visualize this in a coordinate plane, this is as we again read it from left to right, we see it moving down. So we've got this slope down form when we look at negative slope. The zero slope is actually when we find the value of our slope to be 0, which is a special case of a horizontal line, and then a no slope, where we're going to get what we call an undefined slope or no slope, because with our calculation of the vertical line, again, a special case, the vertical line will produce a value that is undefined, which then means there is no slope that exists for that line. And every single slope we encounter is going to boil down to one of these 4: positive slope, negative slope, zero slope, or no slope. So in words, here's what we just encountered: that if the slope of a line is positive, then that line slopes upward. If the slope of the line is negative, then that line slopes downward. A horizontal line always has 0 slope, and a vertical line always has no slope. And we'll again see this unpacked as we approach the slope formula, and then we'll conclude our lesson today by using each of these 3 formulas with some given examples. So we finish off with our analytic formulas by looking at the slope formula. Now again, not every line has a slope, because that vertical line is the exception to this rule. But when a line does have slope, that means we're going to be able to calculate its value. And we can calculate it again by letting the points A and B be the x sub 1, y sub 1, and B be x sub 2, y sub 2. And what we find then is the slope formula below. M is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We like to use M as the letter or the value of our slope. And what, again, by definition, is the change in y's over the change in x. So we have the difference of our y's divided by the difference of our x's, and that gives us then the value of our slope. So now our task at hand for these last 3 slides is I'm going to give you 2 points, and from those 2 points, we are going to calculate the distance, the midpoint, and the slope for those 2 given points, and we'll do that 3 times. We'll actually see this unfold in a couple different ways, and this is also the task at hand, what you'll see on your homework assignment, where I will give you 2 points, and you'll do the exact same thing. You will calculate the distance, the midpoint, and the slope between those 2 points. So let's start with our first example, these 2 points, point Q and point R, with the given values of -3, 5, and 7, 1. So as it turns out, we don't need a diagram to actually calculate the distance, midpoint, and slope. All we need is our formulas. Let's begin with the distance formula. And actually, where I should really begin is by using what our labels were for each of our points that we saw with A and B. So we're going to call this first point here x sub 1, y sub 1, and this second point here x sub 2, y sub 2. And that way then we'll know where to plug our values in. So the distance formula, right? Distance formula is then the square or change in our x values. So x sub 2 minus x sub 1 squared, plus the change in our y values squared, so y sub 2 minus y sub 1 squared. Let's plug in what we know. So we've got then x sub 2 is 7 minus x sub 1, which is -3, squared. We've got y sub 2, which is 1, minus our y sub 1, which is 5, squared. And we're going to then evaluate that. -7 minus the -3 is adding a positive, so that's 10. So we get then 10 squared plus 1 minus 5 is -4, -4 squared. Now, remember, whenever you square anything, squaring anything always makes it positive. So we get then 100 plus 16, and we get a value of 116. Let's see, that is divisible by 4. So 4 goes into that 29 times. And so we get 4 times 29. And from that, we can take the square root of 4, so a 2 pops out front, and then that root 29, 29 is prime, that gets stuck on the inside. So there is our distance between the 2 points, 2 root 29. All right, so that is our first calculation, calculate the distance. We can also calculate then the midpoint. The midpoint is the average of our points. So we do x sub 1 plus x sub 2 divided by 2, and then we'll do comma our y sub 1 plus y sub 2 divided by 2, right? Midpoint is essentially another ordered pair. We can call that point M if we want to. So point M will have the ordered pair of x sub 1, the average of our x values, and then the average of our y values. So let's again plug in our values. So our point M, our value for x sub 1 is -3, plus x sub 2 is 7 over 2. And then we have our y sub 1, which is 5, y sub 2, which is 1 over 2. And then we simplify. -3 plus 7 is 4. And we have that 4 over 2. And then 5 plus 1 is 6, 6 over 2. And then we simplify that, and we get our value of our midpoint is then 2, 3. So that is then the halfway point between these 2 points, the 2 endpoints of our segment QR. So M would then be the midpoint. And then last but not least, we can calculate the slope of this line by doing then the change in our y's over the change in our x's. So one last time, let's plug in our values. So y sub 2 is 1 minus y sub 1, which is 5. And then we have x sub 2 is 7 minus our x sub 1, which is -3. So subtracting that negative, be careful there. So we then simplify the numerator. 1 minus 5 is -4. We simplify the denominator. 7 minus the -3 is adding a positive there, so it's going to be 10. And then we simplify our slope. Each of those values are divisible by 2. And so we get a final value for our slope, -2/5. So there we have it. There is our slope. There is our midpoint, and there is our distance, using those analytic formulas for the equation of, or for the plotting 2 points in a plane. So we're just going to repeat this. We'll see a second example and a third example, basically just following through, calculating the distance, midpoint, and slope of any given 2 points. So let's then do another. We've got points S and T. S is 7, 4, and T is 7, -4. Let's go ahead and then assign, that's x sub 1, y sub 1, x sub 2, y sub 2. And actually the beautiful part about ordered pairs is I could call point S the x sub 2, y sub 2, and point T the x sub 1, y sub 1, and I would still have the exact same answers each time. The one thing you don't want to do is mix match your subscripts. Don't do like an x sub 1 and then a y sub 2. Don't do that. You want to make sure it's all your 1s are paired and then all your 2s are paired. So we're going to do basically the exact same thing, distance formula. Now I'm going to go ahead and skip the distance formula, just jump right into the theatrics of the calculation. So we have x sub 2 minus x sub 1. So we have 7 minus 7, which actually we'll see is going to be super nice to us, squared, plus we'll have then y sub 2 minus y sub 1, so -4 minus 4, square that. We then end up in our first calculation, 7 minus 7 is 0, so 0 squared is an easy calculation. -4 minus 4 is -8 squared. We end up with then 0 plus 64, right? Because whenever you square anything, it is then always positive there. And so then we add 0 to 64, we get square root of 64, which then just turns back into 8. So we get then our distance between these 2 points is just simply a length of 8. Now, if you visualize this, these 2 points are actually on the same vertical line. And so by visualizing that, we could have actually just counted the number of units along the vertical to get from one to the other, which would have then been, we find the length of 8. So there's our distance. Let's do our midpoint now. So again, the midpoint is the average of our x and y values. So we have then the x sub 1 plus our x sub 2 over 2. And then we have our y sub 1 plus our y sub 2 over 2. And we see it's going to be actually super nice to us. We have 7 plus 7, which is then 14 over 2. 4 plus -4 is actually 0 over 2. And then we simplify this, we get our final answer for our midpoint. 14 over 2 is 7. 0 over 2 is just simply 0. So there is the midpoint then of our ordered pairs, 7, 0. And last but not least, we will calculate the slope. Now, this is where things get interesting with our slope. Remember, it's always going to fall into one of the 4 categories. It's either going to be positive slope, negative slope, no, zero slope, or no slope. So let's see what happens. So we do the change in our y's, so -4 minus 4 over the change in our x's, 7 minus 7. Uh-oh, let's take a look, see what happens there. As we then see what follows, -4 minus 4 is -8. 7 minus 7 is 0. Let's take a look at that. Uh-oh. We end up with then an undefined slope because -8 divided by 0, we can't divide by 0. So this is a situation where we have no slope, right? There's actually an undefined slope to this, and that's always our special case with the vertical lines. We will not have a slope with that one. Because again, we can't divide by 0. So there we have it. From those 2 points, we were able to calculate its distance, the midpoint, and also then come to the conclusion that it does not have a slope to this special case, the vertical line. Let's do one more example, and we make it a little bit trickier. Let's make our vertices, or the endpoints here of our segment, some fractions. And so we'll practice with our fractions with some operations. So again, we can assign x sub 1, y sub 1, x sub 2, y sub 2, and then we'll work at putting these together. So we have our distance formula, which again, I'll skip the theatrics of writing down that formula again. We'll just begin plugging in our values. So I do x sub 2, which is -1/2, minus x sub 1, which is -1/5. And we've got to square that. And then we have plus our y sub 2, -2, minus our y sub 1, which is 7/10, and we square that. And then we are going to simplify that, which means we're going to need common denominators. So the common denominator between the -1/2 and the 1/5 there is a denominator of 10. And then also with the -2 and the 7/10 is also a denominator of 10. And so we can then get common denominators. Our first set of fractions here is going to be -5/10 minus 2/10, which we'll put that together. We'll square that. And then we will add that to -20/10 minus 7/10. So we have to change that one, and we'll square that. All right, so with the first one, we end up then with we have -7/10, right? Because we do -5/10 minus 2/10. We'll square that. We then over here in the next one, we end up with -27/10, and we'll square that. And then we'll get these guys into a common denominator together. So let's go ahead and figure this out here. Let me just grab my calculator. So we get 49/100ths plus, and let's go ahead and square 27, 729/100ths, and we add those together, and we end up with, right, because everything we square is going to be positive, so 49 plus the 729, we end up with 778. Fix that real quick. 778 over 100. Now, with square roots, you can take the square root of the numerator and the denominator, which means we end up with the square root of 778 over 10, because we take the square root of 100, we like that. It's a nice perfect square. And there's our final answer. As it turns out, there are no perfect squares inside of 778. So that is our final answer for the distance. And so, yes, working with fractions, you're going to end up finding the need to get common denominators, and working with squaring fractions, working with square roots of fractions. And so all good stuff with practicing with these formulas. All right, now let's calculate the midpoint of our 2 points, u and v. So midpoint is the average. So this is where things get kind of fun, because we are going to be adding some fractions and then also dividing by 2. So we have the sum of our x values, so 1/5 plus that -1/2 divided by 2. And then we have our average of our y values, so that's 7/10 plus this -2 divided by There we go. Divide by 2. And we are going to then again get common denominators and then add those together. So we get 2/10 plus -5/10, comma, and then we have 7/10, which we're not going to change, plus -20/10, and we simplify that. That's over 2, and that's divided by 2, which we'll divide by 2 at the very end. We'll see it's actually very simple to divide by 2. So we have 2/10 plus a -5/10. That will give us then a -3/10 over 2. And then we have 7/10 plus a -20/10. That's -13/10 over 2. And now to divide by 2, here's the easiest part. Whenever you take anything to divide by 2, or divide by anything, and it's a fraction, all you have to do is just multiply the denominator by that number. So we're going to take our fraction -3/10 and just multiply the denominator by 2, and that's going to simplify that for us. So we get -3/20, and then we also then have -13/20. That's 13. Let me fix that. And there we have it. There is our midpoint M with those fractions. So again, working with adding, subtracting with like terms, and then dividing, all good things with practicing with our values with fractions. Okay, we have one more calculation to make, and that is finding the slope. So the slope is then going to be the change in our y's over the change in x's. So we have the change in a y, -2 minus 7/10 over the change in x's, so -1/2 minus 1/5. It's actually going to turn out to be the exact same numbers we saw in the distance formula. So we get then -27/10 in our numerator divided by -7/10 in our denominator. Now, it looked really awful now. You're like, oh man, what do I do with this? Rewrite this expression. It's really just -27/10 divided by -7/10. All right, and so that's not too bad because you know how to divide fractions. You keep change flip. You then take -27 -27/10, leave it, but then you multiply by the reciprocal -10/7, and then you see we can simplify this. So negative times a negative is a positive. So now we're going to end up with a positive number, right? So those positives will end up. The 10 in the numerator and the 10 in the denominator will cancel out. They reduce down to 1. And then what we're left with is 27 over 7, which again, 7 is prime. It doesn't divide into 27. And so there is our slope. We end up with a positive slope this time. So these 2 points, when we plot, we'll find a positive or upward slope of a line. So there we have it with our last calculation there, finding the slope. And so now, as we revisit the cases we've just countered, we were able to calculate the distance, the midpoint, and the slope, all with fractions. And yes, you'll see some examples on your worksheet where you'll practice with fractions as well. So we've come to the end of our lesson here of our first lesson, 13.1, on our analytic formulas. If you do have any questions on any of these or any of the questions on the homework assignment, please do not hesitate to email me. I will get back with you. With that, be good and do good.